Thank you for the introduction, also for the invitation. I'm very pleased to be here. So today I'm going to talk about the moments of Margulis functions, which is related to the quantitative non-divergence estimate in the space of lattices and its application number theory, especially about the distribution of values of ternary quadratic forms. So the main object I'm going to talk about today is a quadratic form, let's say in n variables given by aij, xi, xj. And here I'm interested in the quadratic forms of real coefficients. Also indefinite and irrational in a projective sense, meaning that Q is not proportional to any rational form. And there's a conjecture by Oppenheim, proposed around 1930. And basically the conjecture asks about the distribution of the values of quadratic form at integer points, whether 0 is isolated in this image or whether the image is dense in the real life. And the conjecture was proved by Margulis in mid-80. So the statement is the following. For any indefinite irrational quadratic form of variables at least 3, the image set at the integer points is dense in the real line. Of course, we need to assume that Q is indefinite and irrational, otherwise the image set would be discrete, so it will never be dense in the real line. And this condition n at least 3 is less obvious, but remark, the statement is not true for n equal 2, because if you take a binary quadratic form like x squared minus 1 plus square root of 3 squared times y squared, then 0 is isolated in the image set. This follows from the fact that this number 1 plus square root of 3 is a badly approximable number in the sense of Diophantine approximation. So let me briefly describe. So the proof of Margulis relies on the homogeneous dynamics. So we used homogeneous dynamics. Let me describe how this problem is related to homogeneous dynamics. So yeah, first of all, it's not very hard to reduce the problem to n equals 3 by looking at the 3-dimensional sections. So let me take the Lie group equal S3R. My lattice gamma is SS3Z. And the homogeneous space G mod gamma is basically the space of 3-dimensional lattices of covolume 1. And let me fix a standard quadratic form of signature 2-1. Say y squared minus 2xz. Then for any quadratic form of signature 2-1 of determinant 1 up to scaling, we can parameterize such quadratic form by in terms of the elements in SS3R. So for any such Q, you can find the element in SS3R such that Q is the Q0 times GQ as a linear transformation. And let me consider a subgroup of G denoted by H by the stabilizer subgroup of this quadratic from Q0. And this is actually asymptotic to SO2. And the relation to the Oppenheim conjecture is the following. We are interested in this image set. By this relation, it's same with the image of the lattice GQZ3 under the quadratic from Q0. And again, Q0 is invariant under this H. One can identify the lattice GQZ3 as a point in the homogeneous space G mod gamma. So this means that if we manage to understand the behavior of H orbit in SS3R mod SS3Z, then we'll be also able to understand this image set. And here is the orbit closure theorem of Daniel Margulis, 1989. The statement is that any H orbit in SS3R mod SS3Z is periodic or dense. So there are only two cases. And moreover, this theorem implies that the period case happens only when our GQ is H times some rational element. So this orbit is dense if and only if Q is irrational. So the periodic orbits amount to rational quadratic forms in this parameterization. So if our quadratic form is given irrational, then the corresponding H orbit will be dense. This means that this image set will fill up the whole Euclidean space. So the image set must be dense in the real life. This is the outline of the proof of the Oppenheim conjecture. And the key thing was this orbit closure theorem. So, yeah.
It came later than the proof, no?
Yeah. So actually, Margulis proved this theorem by proving a weaker version of this theorem, and he strengthened the statement with Dani in 1980.
Can you explain what is stabilizer of Q naught?
So we have SS3 actions on quadratic forms in that sense.
Exactly that one special if we ought to preserve the quadratic function.
Is there any other question? Then let me move on to the quantitative version of this type of questions. So for the quantitative version, we consider counting function for the number of integer vectors of size n most capital T, such that the the value of quadratic form at this point falls into the interval between A and B. So the original Oppenheim conjecture amounts to the statement that for any given interval A and B, the discounting function goes to the infinity as T goes to infinity. As a quantitative version, we are interested in the asymptotic of this function, discounting function, as the size parameter capital T goes to the infinity. So yeah, we can make a guess for the asymptotic. Instead of the integer point, you can think of the region satisfying these two inequalities. If we try to compute it's not very hard to compute the volume of this region. It's actually some constant only depending on the quadratic form Q times the length of the interval times e to the n-2. So it is natural to expect that our counting function, as it's the counting function for the number of integer points contained in this region, it's natural to expect this counting function should follow the same asymptotic b2 times b minus a times e to the n-2. And this is called the quantitative version of the Oppenheim conjecture. And I think the first major development was made by Dani and Margulis, again, in 1993. They established the lower bound of the asymptotic, namely the counting function divided by t to the n-2 is only the expected lower bound, the expected number c2 times b minus a. But the upper bound for this asymptotic is more subtle because actually it depends on the signature of the quadratic form. So let me write our quadratic form is of signature PQ, and P is at least 2 and Q is at least 1, as Q is indefinite. For upper bound, Eskin, Mozes, Margulis in 98 proved the upper bound for other forms of signature, except for signature 2-1 and 2-2. For such signatures, they prove that the asymptotic of the counting function is as expected. But for signature 2-1 or 2-2, the situation is more complicated because this asymptotic actually can break down. And there are two scenarios that the asymptotic can break down. First, if our Q is very close to a rational form, okay, for a rational quadratic form, the image set would be discrete, and Q is, even if Q is rational, if it is very close to a rational form, then the image set could be still very much concentrated around integer points. So if you take your interval A and B to contain an integer point, then there could be, there might be so many points, much more than the expected, then the expected asymptotic would break down. Also, if Q has a large isotropic subspace, large meaning that dimension n-2,
Why do we say that it's n-2 by n-2?
n-2 here. So our Q is quadratic. The size of the value is more or less t squared, and there are t to the n many points inside this board. So if you assume they are more or less well distributed, then for a given interval, the size of asymptotic should be t to the n divided by the size of
What does it mean to be very close to a rational?
In a metric Diophantine approximation sense for the coefficients. So in a sense that Q is very close to some rational form. Of course, this Q prime might have a large coefficient. Something like this for a given number, given large exponent capital N. So in a sense of metric Diophantine approximation for the coefficients of the quadratic form. And the second scenario, if Q has large isotropic subspaces, then this large isotropic subspace already contains t to the n-2 many integer points. So if A and B, the interval between A and B contains 0, then no matter what A and B are, the discounting function already is already at least some constant times t to the n-2, so the asymptotic breaks down.
On the n-2 dimensional isotropic subspace, you don't see if the signature is anything other than 2 or 2. So.
This case?
Yeah.
Yeah. Okay, so Eskin, Mozes, Margulis also established the case of the signature 2, Of course, without any assumption or adjustment, the asymptotic will not hold the same. So we definitely need some assumption. So to avoid the first scenario, we should assume Q is not very close to rational form. The asymptotic is as expected, up to some adjustment for the counting function. What is the adjustment? This counting function counts the points not on isotropic rational isotropic planes. In order to avoid the second scenario. And this assumption and this adjustment of the counting function is necessary, otherwise the theorem doesn't hold, as the reasons we mentioned earlier. In the main theorem I'd like to present today is the case of signature 2-1. In this case, so of course, for this case, n is 4, so the asymptotic should be t squared. In this case, the asymptotic is as expected, and Q tilde again counts the points on not on such exceptional subspaces.
So lines, right? In this case.
Lines, and there are also exceptional planes. Actually, there is another reason, that the asymptotic might break down. If there's a rational plane such that the restriction of this quadratic form Q at that plane becomes a perfect square, then that might also be a problem. So one needs to exclude isotropic lines and such degenerate planes. And the remark, recently, there's another amazing related result by Strauss. Mohammadi, Stephen Wang and Lei Yang. They proved the power saving error term for this asymptotic. So the error term would look like big O of t to the 1 minus some power saving. And this result follows from their effective equidistribution theorem in SS3R mod SS3Z based on their recent breakthrough on effective equidistribution. So this is the statement of the main theorem. Is there any questions so far?
I'd like to follow up on his question. So the volume, when n is equal to 2,
Yep.
the volume, the formula suggests that it will be constant, but I think it will be logarithmic in the volume of VQ.
In that case, the conjecture, the original conjecture is not good.
Yeah, but I mean, this has nothing. This part of the
Volume you can still compute, right?
volume you can still compute. So the question is like, this logarithmic is just n equal to 2, or does it disappear, or maybe I'm wrong and there is no.
The logarithmic factor presumably depends on the fact that the SO, so it's in that case, it's an SO 1, 1. That's right. It's a diagonalizable subgroup. This is, so the group here is a semi-simple group. So you should really expect something like polynomial growth instead of logarithmic.
Yeah, I was not thinking about the group. This is just a question about hyperbolas, volume.
I think the volume itself should be logarithmic, but I mean, yeah, then depending on the choice of intervals or the Diophantine property of the quadratic form, the expectation for discounting function would be more complicated. As for this case, the Oppenheim conjecture is not even true. It's not even dense. So it should depend on A, B, and capital Q. But
Yeah, so
I think
my
the
question is
volume
really stupid. Like this formula for the volume seems to not be correct when n equal to 2. And
yes.
then is it still correct for higher n? Because you kind of add dimensions, so you should be getting factors of t on top of the logarithm. You're still kind of going. Okay, yeah, as you pointed out, it's quadratic, right? So you look at the level curves, level surfaces, and then you go towards it with some rate, which is 1 over t. Okay, never mind. Sorry.
Okay. I think so. Yeah, all these results rely on homogeneous dynamics, as in the original Oppenheim conjecture. So let me describe how this quantitative Oppenheim conjecture translates to problem of equidistribution problem in the space of lattices. So let me introduce two subgroups in this H, SO21. Let me take a diagonal subgroup of H given by e to the t1, e to the negative t, and take a unipotent subgroup 1 r squared over 2 like this. These are contained in the subgroup H. And for simplicity, let me write the associated lattice GQ-3 as delta Q. And let me go back to the idea of Dani and Margulis, which established the lower bound for a parameter t equal log t. We observed that the counting function can be written as the orbit integral for a certain test function capital T. So here, delta Q is the associated lattice to the quadratic form Q. We take a unipotent translate and push it forward by the diagonal element AT. Then this unipotent subgroup is expanded by the diagonal subgroup. So it's a very long trajectory evaluated by certain test function capital F. And this capital function, this capital F is roughly the Ziegler transform of the indicator function on the region of given by the intersection of the unit box and the inverse image of the interval A and B. So up to some smoothness issue, our test function capital F is an indicator function, a Ziegler transform of the indicator function, and the Ziegler transform is basically the counting function for the number of lattice points contained in this region in the Euclidean space. So they observed that the counting function can be written as the equidistribution problem with respect to the Ziegler transform. And in the same paper, they proved that they combine the reference equidistribution theorem and the linearization method developed in the same paper. If we take any bounded continuous function and any irrational quadratic form Q, then the corresponding orbit integral converges to its average over the whole space. So if we are able to apply this theorem for this Ziegler transform capital F, then we would be able to establish the quantitative Oppenheim conjecture. Unfortunately, this is not possible because the Ziegler transform capital F is unbounded. Of course, even for unbounded test function capital F, you can decompose the test function into two parts, compact part and cost part, and by taking a cutoff function. And for the compact part of the test function, you can still apply the reference equidistribution theorem. But there might be some contribution from the orbit integral around the cost. So one needs to control that contribution, and this amounts to the quantitative non-divergence. So basically from the contribution from the compact part, one can immediately deduce the lower bound. And there was exactly what Dani and Margulis did for the lower bound of the asymptotic, but for upper bound, one really needs to establish the equidistribution for unbounded test function. So in more general context, we need to answer this question: for which unbounded test function F does returns distribution theorem still hold. So more generally, if you want to apply the reference equidistribution theorem for unbounded functions like Ziegler transform like here, or Eisenstein series or theta functions, you would end up with the same type of question. So yeah, to sum up for the upper bound, we need some quantitative non-divergence result for this type of unipotent orbit in the space of lattices. And also, to expect the generalization of reference theorem for unbounded test function, we would definitely need some type of growth condition, because otherwise, if our test function is given like if it diverges to infinity with exponentially fast speed, then the integral will just diverge from a very small contribution of the, as soon as it visits a very small part of the cusp, it will just diverge. So some growth condition is required to expect the generalization of reference theorem. So to sum up, we need to quantify the growth of the, or quantify the distance to the cusp by some function, and this can be done by Margulis height function.
So what exactly?
Yep.
Just to understand the question, what exactly do you want from the? What is the statement of Wagner's distribution that you?
Yeah, I will write the statement in terms of this Margulis function.
Okay.
So let me take an n-dimensional lattice, delta, and so I want to quantify how far this lattice is from the infinity in the space of lattices. For each dimension between 1 and n-1, let me define function alpha I by the inverse of the co-volume of the I-dimensional sublattices, I-dimensional rational subspaces. So your R is I-dimensional rational subspace of contained in the lattice delta. So for I equal 1, it's just the inverse of the length of the shortest vector. So
But
yeah.
shouldn't it depend on L? What do you mean by it?
So, oh, I'm sorry. So it means by taking the supremum, I'm sorry. So yeah, for I equal 1, it's really the inverse of the length of the shortest vector. And I simply take my Margulis alpha function by just the maximum or alpha i's. Then this is a nice height function in the sense that alpha of delta goes to infinity in the space of lattices, if and only my delta goes to the cusp in the space of lattices. Okay, here is a fact. It's called Lipschitz principle. to connect the Margulis function and the test function I mentioned earlier, the Ziegler, any Ziegler transform of a continuous function in the Euclidean space is dominated by the Margulis function alpha there. So in the end, we would like to establish the Latour's equidistribution theorem for unbounded function controlled by this Margulis alpha function. Let me, I will write the more precise statement. So the key ingredient for the quantitative non-divergence result for 2-1 case is the following. If I assume the same thing, Q is not very close to rational, and also if I assume if it doesn't contain almost isotropic integral vectors, then there exists an exponent lambda bigger than 1 such that the moment of alpha function integrated over the same orbit AT UR delta Q is uniformly bounded regardless of the shift AT. I just make a remark such that for this type of uniform boundedness result, in Eskin, Mozes, Margulis, they showed this type of result for any irrational Q or even for rational Q and exponent lambda less than 1. So basically, this uniform boundedness result controls the quantitative non-divergence of this orbit. More and higher for higher and higher exponent lambda. Once we have this uniform bounded result, then it means that we would have a better and better quantitative non-divergence bound. And this exponent 1, the improvement upon 1 is important because the test function we'd like to apply is dominated by capital alpha, the alpha to the exponent 1. So there's a corollary of this uniform boundedness result. So if my continuous function f is dominated by alpha, then Latour's equidistribution theorem holds for this class of test functions provided closed condition. Is there any questions so far? So
What does it mean exactly? The statement like not very close to rational and does not contain almost isotropy.
Yeah, the same assumption here for
almost isotropic we
this
haven't
cube.
defined, right? Almost isotropic we haven't defined.
In the sense of I haven't defined, in a similar spirit to this sense, Q evaluated the integral vector is bigger than some constant times the size of integral vector to the large negative exponent.
But no, yeah, but in terms of like Q is not very close to rational in terms of what, which parameter?
In this sense,
There exists C and M.
there exists constant C and capital M such that for any integral quadratic form Q prime, and of course up to some scaling, it's not close to any
So
integral Q primes. It's a metric Diophantine sense. Yeah, a simple example is probably if you take the quadratic form as x squared plus y squared minus square root 2z squared, or if you take any quadratic form of algebraic coefficients, which is not rational, then they are not very close to rational point because any algebraic number is not very well approximable by rational numbers.
okay, and C and M are like absolute, just what are C and M?
Yeah, and it's more constant C and say large exponent capital N.
Okay, allowed to depend on Q, right?
Of course, yeah,
It just
independent of Q prime.
yes.
Yeah, so this uniform boundedness star is the key ingredient for the proof of this quantitative Oppenheim. So maybe of its proof.
F to grow slightly faster, right? Then
Mhm.
you can presumably you can allow F to grow slightly faster than alpha.
Yeah, alpha to the 1 plus some epsilon also allowed.
1 minus lambda. Same lambda. Yes. That's it.
Okay, so the sketch. Yeah, so let me go back to the paper of Eskin, Mozes, Margulis, which proved the similar result for the exponent lambda less than 1. So for the key ingredient is so-called Margulis inequality, which is kind of subharmonic estimate for that height function alpha. So for any exponent lambda less than 1 and a time parameter s, and any starting point in G mod gamma, this is for Margulis inequality. if you take an average over the orbit ASUR delta for the height function to the lambda, then it's controlled by some vector less than 1 times the alpha value of the original starting point delta to the let's say 10s. It's not optimal, but the point of this estimate is that the coefficient here is 1 minus lambda. The coefficient here is less than 1. So whenever, on average, over the unipotent orbit R, whenever you take push forward orbit by AS, the value of alpha to the delta is subharmonic. So alpha of delta is given very large, then it should decrease on average. And actually, Eskin, Mozes, Margulis proved the estimate star for lambda less than 1 by iterating this inequality for many times. So yeah, no matter how many times you iterate this inequality, the given by the fact that this constant is less than 1, the moment integral of alpha to the lambda remains bounded. However, for lambda bigger than 1, this vector gets bigger than 1. So there's no contraction for the average of alpha to the lambda. So to extend the result for lambda beyond 1, we need some modification. So for delta, small delta, I take or lambda, the 1 plus 3 delta. And I'd like to construct a modified alpha function and call it alpha tilde. Going to from G mod gamma to 1 to infinity, such that it satisfies two properties. So this modified function measures alpha to the 1 plus 3 delta. And second, it satisfies a modified version of the Margulis inequality. So if we take an average over the integral ASUR delta for this modified Margulis function, it still has a contraction with a rate e to the negative delta s. So the Margulis inequality holds for this modified function. Of course, this Margulis inequality doesn't hold for lambda bigger than 1, so there should be some cost. So this estimate holds only for, except for delta contained in some exceptional set. When our lattice delta contains almost isotropic vector, so a vector very close to the right cone, given by the locus of the standard quadratic from Q0. Yeah, let me call this exception set epsilon. And yeah, this exceptional set epsilon is of a very small volume in G mod gamma. So another ingredient is that for most of R, whenever our delta is outside this exceptional set, we would have this modified version of Margulis inequality. It means that we should also need some control for the exceptional set, in the sense that if you look at long unipotent trajectory, then only a small portion of R, of course, in a quantitative sense, can be contained in this exceptional set. This borrowed from effective avoidance principle. Yeah, one can view this exceptional set as a thin neighborhood of some manifold contained in G mod gamma, and one can explicitly describe the shape of this exceptional set, and more specifically, I use the effective avoidance estimate of Song and Sanchez. And the proof of star follows from combining these two ingredients. So we divide the time t to many stable intervals from S1 to Sn, and we wanted to bound alpha to the 1 plus 3 delta integral. And one can write this ATUR as a iteration of random walks. ASN, URN, AS1, UR1, delta. One to PRN. And by the effective avoidance principle for most of alpha 1 to alpha n, the iteration of the random walk is not contained in the exceptional set. So the contribution of exceptional R1 to Rn is very small. And for rest of R1 to Rn not contained in the exceptional set, we applied this modified version of Margulis inequality, and combining these two ingredients, we would end up with the proof of this uniform boundedness result. And this in turn implies the generalization of Returns theorem for unbounded functions. And eventually we get the quantitative version of the Oppenheim conjecture for the signature 2-1. So yeah, I stop here. Thank you very much.
Questions? First of all, so basically lambda equals 1 would be enough, right, for the application.
Actually, you need any lambda strictly bigger than 1 is enough. If you only have lambda equal 1, you know that the supremum is bounded, but it would only imply that this integral is bounded. You don't know where it really converges. There might be some non-trivial contribution from the cusp. If you only know this for lambda equal 1, that contribution is not infinity, but might be still positive. It's not infinite.
And and of course, you need that Q is not close to rational in order to get off.
Yeah, sure. Yeah,
For the-
assuming the same thing. This square. Yeah.
Got it. What's the definition of this alpha delta tilde, roughly?
Roughly, so for n equals 3 case. Yeah. So then let me go back to alpha 1, alpha 2 for the original alpha 1, the supremum was taken by the inverse of the shortest length. For this modified alpha, I take instead of just the inverse of the length, I take some function phi, and the supremum is taken for the lattice point contained in the unit box. And the shape of the function phi is basically similar with this function, but with some Diophantine vector kappa. And this kappa basically, I don't write it explicitly, but kappa is more or less the distance to the light cone Q0 equal 0. So that Margulis inequality follows from the corresponding Margulis inequality with respect to this function in the representation space. So first I prove the Margulis inequality for this modified local height function phi. And actually the original Margulis inequality fails when the V is very close to the light cone. But with this modification, one can still show that the Margulis inequality still holds for this phi, and this implies the global Margulis inequality for alpha tilde with this construction. This is roughly the shape of the modification.
All right, let's conclude again.